Good morning, everyone. And as Aisha mentioned, this summer I worked with Dr. Oliver Boyd down at USGS to develop a Petrologic database for the USGS National Crustal Model, which is a lot of jargon, I know. So I'm going to start out today talking to you about earthquakes and seismic hazards. And really, to get a good grasp of what a seismic hazard is, you've got to understand the difference between seismic hazard and seismic risk. Now, a seismic hazard is a phenomenon that's capable of producing property damage or loss of life, so the ground motion that's associated with an earthquake. The risk, on the other hand, is the probability of that phenomenon causing substantial property damage or loss of life. So the probability of a building falling is your risk associated with your seismic hazard. One of the greatest illustrations of this was actually in the 1906 San Francisco earthquake that caused about $400 million in 1906 of damage. Now, there was a lot of damage in San Francisco itself. However, 55 miles to the north in Santa Rosa, which was actually further from the source of the earthquake, devastation was total. There wasn't a single building left standing. And so the question, of course, becomes, why was it so much worse in Santa Rosa? It was further from the source. What's the difference? There's a lot of things that contributed to the difference in damage between Santa Rosa and San Francisco. But one of the biggest things comes down to a difference between cake and jello. So hard rocks, like much of San Francisco, are denser. And so seismic waves travel much faster through them. So the ground shakes for less time overall. And this is less ground motion overall also. Soft rocks and sediments, like in Santa Rosa, are much less dense, like jello. And so the seismic waves slow down, and the shaking lasts for a much longer period of time. And this is more ground motion overall. This is what's known as site response. So you're probably thinking, okay, so there's seismic hazard associated with earthquakes and faults. How do I know what my seismic hazard is, and what can I do to mitigate it? So for the last 40 years, the United States Geological Survey has been producing these national seismic hazard maps. Now, it's important to note that these don't predict when earthquakes are going to happen. What these do is they predict the probability of a certain size event occurring within the next 50 years. This is the current 2014 National Seismic Hazard Map. And what these hazard maps do is they incorporate what are known as ground motion models to predict the amount of ground motion associated with an earthquake. And then they feed those ground motion models into probability simulations to calculate the probability of that event happening within the next 50 years. One of the key components of any ground motion model for the last 20 years is what's known as VS30. Now, this is the time average shear wave velocity to a depth of 30 meters, which is jargon again. But basically what this tells us is how fast these seismic waves are going to be moving in the top 30 meters of the crust. So this is the superficial geology, and this is telling us how fast these seismic waves are moving through cake or jello. And the really nice thing about these VS30 values is that we can actually measure them. And we have measurements across the United States, so we can test our calculations from these measured values. Now, you'll remember the previous slide with the National Seismic Hazard Map. There were a lot of really rounded contours, and it was really well distributed. This is the geologic map of the United States. This shows that superficial geology all over the country. And you can see that it's really complex, and there's a lot of differences. And if you zoom in, it actually gets even more complex. Your eye tricks you with the zoomed out version to smooth out the colors and to average it. So the real question is, how do we incorporate the differences between the superficial geologies into our ground motion models? Because the current version of the National Seismic Hazard Map just assumes a uniform site condition across the entire country. That's where the National Crustal model comes in. This model is another ground motion model that's been in development for the last few years. And what it does is it incorporates a sediment depth profile, a sand silt clay profile, a porosity profile, and a petrologic profile. Now, this is all of that surface geology, and it creates a new ground motion model based on all of that surface geology. What I worked on this summer was the database that the petrologic profile is going to draw from. So you're probably wondering, okay, so it's a database. Where did it come from? What is it? The database itself consists of 209 geologic units initially, and all of these units were pulled from the legend of that National Geologic map that I showed you a couple slides ago. So what do we need to know about each of these units? So we need to know what minerals are in each of those units, and that can be defined by rock type in most cases. And we also need to know what volume of these geologic units each of those minerals takes up. And then because there's natural variation within systems and within rock types, we need to kind of get a range of compositions for each unit so that we can do error analysis in the calibration setting. So how do we define these units? Well, for the precisely named rock types, you know, your standard igneous rocks, metamorphic rocks, and sedimentary rocks like granite and arkose and blue schist, we just use standard nomenclature from literature. There are, however, other field mapping units on the geologic map that are general sediments and sedimentary rocks, so alluvium and sandstone, and depositional environments, so playa, delta, melange. These things we have to rely on a level of interpretation to determine the rock types that would actually develop in those depositional environments. So in addition to compiling all of these definitions, there's also some metadata associated with the database itself. So I wanted to really describe what kinds of units we have. As I mentioned before, in the legend, there were 209 geologic units. However, when you actually go to the map and search it, there's only 164, which leaves 45 units that aren't actually present on the map. Now, of those 45 units, 13 of them were actually really specific rock types, things like gabbro or monzo-gabbro and syenite. And so those are really easy to define, and I went ahead and defined them. So we have a total of 177 geologic units defined within the database at this point. We also wanted to have a good idea of what percentage of the database each rock type made up. And so we split the rock type, the geologic units up into 5 different categories. You have your basic sedimentary, igneous, and metamorphic rocks, and then also sediment, and as mentioned before, those field mapping units. And you can see that 36% of the database are those general sediments and those field mapping units. Now, in addition to the development of the database, I was able to actually start on the calibration. And as I mentioned before, VS30 is a key critical component, and we have measured values for it. So in the Western United States, we have almost 3,000 data points for VS30 measurements. Most of those data points occur in the areas represented by these pink stars. And so by taking these individual data points and overlaying them with the geologic map, you can determine which data point sits in which geologic unit. And this will give us an average of about 70 data points per geologic unit. So you take an average of those VS30 values, and then you extrapolate that across the Western United States, and you come up with this map. Now, the darker, more contrasted colors, those are the units that have some representation of VS30 values. You'll see these washed out kind of light yellow units, and those are geologic units in which we don't actually have any data for VS30 values. But looking at the map as a whole, you can see that there's pretty good coverage for the Western United States, which is good news because it'll help us calibrate our model further. So moving forward, before we can actually apply the National Crustal model to the National Seismic Hazard Map, we need to make a few updates to the map, the geologic map, and most of that will be in redefining and kind of refining the definitions of those field mapping units and the general sediments. In addition to this, there's some minor refinements that need to be made to the database. We're going to go ahead and remove those units that aren't present on the map and that aren't really well defined. And then there's also going to be minor adjustments to the volume fractions to better match our calculations to the ground truth data. And finally, the calibration is an ongoing process where we're comparing our measured VS30 values to our calculations of porosity and velocities and then densities also. Finally, I'd like to just take a second to thank our NSF sponsors, NUNAVCO and RESESS, and especially our graduate student assistants. And I can open up the floor now to any questions. Jackie, you're always behind.
So, Theron, that was great, thanks. Why not just use the VS30 data to calibrate in the hazard maps then? Why do this?
There are other factors that they feed into the ground motion models, so P-wave velocities and then different porosities. And VS30 are, so yes, there's 3,000 data points, but there's 300,000 geologic units in the national map. And yeah, and VS30 measurements are actually really expensive. And they're normally only done when you're building something like a hospital, and there's millions of dollars pouring into the hazard response for that specific site of interest. So we need to be able to calculate VS30 and then compare it to the sites where we do have data,
I see.
because it's so expensive to actually, you have to drill a hole. And that's
so
a very
it's great
expensive.
as a calibration tool for your larger
Yeah,
geologic map petrographic
exactly.
determinations. Awesome. Thank you.
Other questions?
For removing the sharp contacts at state borders, is that referring to like when you showed that map of the whole, like, wait, what was it? Like the Crustal model, I guess? Like I noticed some states
Yes.
that, like at the state line, like you could just see the state line, like New Mexico to Texas and like Colorado and stuff. Yeah, so like how does that happen? Because
So this is a compilation map. So what it does is it feeds in all of the existing digitized maps from the entire country and assigns values. It was a very complicated process. There's a lot of like metadata around it actually. But obviously there's some smoothing that needs to happen around these sharp contacts. And most of the time it's actually small differences. So it'll be like alluvium on one side and then colluvium on the other side. And so it's just a matter of figuring out which it actually is and then updating the shapefile.
Mary.
I was curious what platform or software the database resides on, and also if there's going to be, what will access for researchers look like in the future?
So currently the database is in Excel format. It was just the easiest way to compile and sort and do everything. So the program itself is written in MATLAB, and all of this is going to be released with an open file report and an online digital supplement on the USGS.
Other questions? No? Thanks, Theron.
Thank you.